Hello. Today we'll be talking about variational autoencoders. These get their name from their ability to perform a certain type of variational inference. But today we'll be talking about their use as a generative model, where you can sample in their latent space and generate out new data points that are distributed like your original data points, no matter how high dimensional or complex the original data distribution is. When we're speaking of generative models in machine learning, we're usually thinking of something like this. A model where you can input noise, which is easy to sample from because you can sample from something simple, like a uniform or a Gaussian distribution to get noise, and then you have something complicated like a neural network that turns this noise into a sample that looks like it's from your training data. And this has numerous uses, including data augmentation, and basically new data entity creation for artistic purposes, etc. So how can we use an autoencoder to do this? The basic gist is that you would want to use just a decoder somehow. Remember that in an autoencoder, you have input data that is some high dimensional vector, for example, and then you send it through an encoder, which compresses it usually into an encoded vector. And then the decoder decodes it back out into the original space, but often without noise or with some augmentation. But what you want to do here is throw away the encoder and just simply sample in this latent space. And then there's some hope that when this gets decoded, it's a new data point because you didn't start with an original one. You started with noise. Or it's something that's very similar to a data point. Can we do this? It turns out, yeah, we can, but not just off the shelf like I told you here. The problem is you can't just randomly sample noise in the latent space. So let's just look at this two-dimensional latent layer that's encoded these MNIST digits. If I sampled here, for example, the autoencoder would not decode it to anything like a data point because it's not trained to decode out here. It's only trained to decode where there are training points. So in particular, these gap regions can become problematic. Another property that's kind of desirable is, what if you had two different data points, so two different 7s or even a 1 and a 7? If you went halfway between them, you're interpolating in the latent space, but you want that to be an interpolated data point. So a data point that looks like a 1 or a 7 or maybe something in between, but still kind of looks like a handwritten digit. But this kind of disjoint latent space with lots of gaps can't be interpolated. And that's one of the things that VAEs try to fix. So the answer to fixing this in a VAE is basically to give each point a buffer zone so that it kind of starts to fill this space. So in a VAE, basically, the latent encoding is actually the mean and the standard deviation or of a Gaussian. It's centered at some location, and that is the encoding of a point. So if you have a point X, and from that point, the latent encoding actually learns a mean and a standard deviation for a Gaussian in a lower dimensional space. But a VAE is trained so that you sample, whenever you sample from this Gaussian, you decode back to the original data point. So basically what happens is, let's say these data points are different shapes. Okay, the encoder encodes that as a normal distribution with a mean and a standard deviation, and if you sample anywhere in here, it's trained to decode back to this original triangle. So this is training by sampling, which gives data points kind of a buffer zone. But it turns out buffer zones aren't enough to give what we want. So if we have a whole bunch of buffer zones for points, these could all be spread apart. And in fact, they will be if you're just enforcing the reconstruction error, because points that are far away can be reconstructed separately without any confusion. So we need another regularization or something to encourage the latent shape to actually look continuous like this so that we have that interpolation possibility. So here, if I sampled in any of these blue regions, it would decode back out to the blue circle. But once you cross over and you're sampling in this orange region, you decode to this point. So there's no gap that I'm traversing where the decoding is uncertain. You can decode back to something that looks like a data point all throughout this space. And the way that variational autoencoders do that is they have an additional penalty. This is a KL divergence penalty. What this penalty is doing is it's encouraging the encoding of every point to actually just be this specific distribution with mean 0 and standard deviation 1. You might be asking, if every point is mean 0 and standard deviation 1, how could we reconstruct anything? The answer is that this is a penalty that is added to this original reconstruction loss so that they play against each other. So what that means is you have all the encodings of points come close together but not overlap each other to play off the reconstruction with the KL divergence penalty. So together you have both losses. This KL divergence penalty that reshapes the latent space into being continuous, like a single continuous blob, and the reconstruction penalty that still keeps separate regions for separate points here, and it creates this kind of continuous latent space where you can just sample and you won't reach a gap. Particularly if you interpolate between 2 points, you will not reach a gap, and then you can put that point through the decoder and decode back into something that looks like the original data. And this is what the loss function of a variational autoencoder looks like. So, but you might be wondering, we talked about how these are trained. We actually said these are trained by actually sampling here and making sure that the decoder decodes back to the point that it came from. So can we actually backpropagate through this kind of sampling procedure? The answer is no, but we can use a reparameterization trick in order to do this kind of backpropagation. What that is we just add an additional noise input. And that noise is always sampled from a 0 mean, 1 standard deviation Gaussian distribution, and it's just added to the mean and the standard deviation that the neural network learns. And it's using this identity here where you can have a vector z that's sampled from this distribution. If you actually sampled c from a normal 0, 1 distribution and you add it to the mean and the standard deviation. And so this trick allows us to add just an additional noise vector as an input with a variational autoencoder that then transforms the latent mean and the standard deviation into a sample from here. So how do we do the training with resampling? So the variational autoencoder, you can think of the latent space or the embedding layer as being split into 2 parts. One part that's encoding the mean, one part that's encoding the standard deviation, and then you add to that an input, which is noise, and you have these 3 quantities combining to give you a sample in the latent space. In this sample, you train it to decode back to the original data point. And the encoding that you're learning actually for any data point is a m-dimensional mean and an m-dimensional standard deviation, which will encode where in this space this input has a Gaussian ball. And so using that, variational autoencoders have been one of the most successful models for data generation. There are others that may be a little bit more popular, like GANs these days, and there are actually other ways of reshaping the latent layer, for example, with an adversarial autoencoder. But variational autoencoders still remain a very important generative model.